So, hello, a very good afternoon to all, and welcome to my class. Today we are going to discuss basically GOC and POC, right? So far we already cover lots of chapter of advanced crash course, right? So from today we are going to start a GOC POC. We try to finish this chapter and try to solve some PYQ from this chapter in two classes. That is one class today and one class tomorrow. So we are going to summarize all the important topic into the two class alone, right? So let's start with the today's session. That is what we are going to study in GOC and POC, right? So let's see this. Okay. Before this, I hope my voice is audible to all of you, and my screen is also visible. If you face any problem related to this, you can text me so that we can rectify this problem. Right? Okay. So basically, we are going to start this thing. I'm not going to discuss about the IUPAC and something because I assume that you know this thing. So in a lesser time, we are trying to focus only on the important topics on which the questions were generally coming in your previous year, right? So basically, we're trying to cover all the important things, all the important topics, and some hot topic in which the questions were coming from this topic only, right? So what do you mean by the bond figure? So first of all, can anyone tell me what do you mean by the bond fission? So basically, fission means what? Fission means anything that is a breaking. That is something which is break is called as fission. So we have a two type of bond fission. We have a two type of bond fission in our organic chemistry. That is one is known as a homolytic fission, and another one is known as heterolytic fission. So what do you mean by this term homolytic fission and heterolytic fission? So, as the name suggests, homolytic fission. So, do you mean by this term homolytic fission? So, homolytic means homo. Homo means something which is consist of a same kind something, right? Like we already studied homogeneous, homolaptic. So, homo means something which is the make of same kind, right? So, in this homolytic fission, each atom separate with one electron, leading to the formation of highly reactive entities called radicals owing their reactivity to their unpaired electrons. So in homolytic, for example, you can see here, this is a homolactic. So in homolactic, what is happening? Let us assume if the bond between the A and A is formed, A and A were formed by the single bond. So we know that in a one bond we have a two electrons. So if the bond break in a such a way that the each one electron are taken away by the two atoms of the molecule, then it will said to be a homolytic fission. So we get the two free radical, right, which is a highly unreactive because due to presence of one unpaired number of electrons. So like this, we can say that in this bond we have a two electrons. So one electron is taken by this A and one electron is taken by this A. So the formation of two free radicals takes place. Free radical means uh, basically the atoms which contain the unpaired number of electrons, we say free radical formation takes place. Now, heterolytic fission basically arise when the two of the atom in either one of the atom is highly electronegative. Right. So if the two atoms which are of same nature, same electron like a diatomic molecule, N2H2O2, in this particular homolytic fission will takes place. But if I'm talking about the atom or molecule like HF and this type of molecule in which the electron activity difference is present. So the molecule in which the electron activity difference is present, in such molecule, the breaking of bond in a such a way that no, electrons were taken by the highly electronegative element. So both the electrons are taken by the only one atom of the which is a highly electronegative in nature. For example, if I'm talking about A and B, suppose B is a more electronegative, then this takes both the two electrons and they become an ion and the A become cation. So in heterolytic fission, one atom holds on to electron, leaving none of for the other, right? So yes. So leaving none for the others, the result in the above case being a negative and positive ion, and respectively the result being the formation of an ion pair. So then this the ion pair formation takes place. So I hope this is very much clear to you. That is what the homolytic and heterolytic fission. For example, we can also say in case of Cl2 molecule, right? In case of Cl2 molecule, Like we have a two different Cls. So each of the electron were taken away by the 1 chlorine atom, and the formation of two free radical of chlorine will be takes place. Now, in case of CH3Cl, so we know that CH3Cl, Cl is much more electronegative than Cl. So there the formation of CH3 carbocation, and this will be Cl negative, that is an anion. So formation of the cation-ion pair will be takes place. So the this one is known as heterolytic fission, right? So this is an example of keep it. So this is an example of heterolytic, where this is an example of homolytic, right? So one is an example of heterolytic fission and one is an example of homolytic fission. So these are the example of the bond fission. So I hope this is clear to you. No problem in this. Okay, good. Now, reaction involving radicals tends to occur in the gas phase and the solution in the non-polar solvent and to be catalyzed by the light and by the addition of other radical. So the reaction involving the radical, in which the free radical will be formed. So reaction involving the radical tends to occur in the gas phase. So this point is very important to note. So this occur in the gas phase only and in solution in the non-polar solvent and be catalyzed by the light and by the addition of other radical. Now, the reaction involving ionic intermediate takes place more readily in the solution in polar solvent because the greater ease of separation of charges therein very often because of the stabilization of the resultant ion pair through solvation. So basically, if I'm talking about homolytic and a heterolytic, so homolytic fission, right? So if I'm talking about the homolytic fission, so they basically occur in the gas phase and in the solution of non-polar solvent and be catalyzed by the light and the other in the addition of other radicals, while the reaction involving the heterolytic takes place more readily in the solution in the polar solvent because of the greater ease of separation of charges there and very often because of the stabilization of the resultant ion pairs through solvation. Right? I hope this is clear to you. Now we are going to study the electronic displacement in the covalent bond. So basically the following four types of electronic effect operate in the covalent bond. The one is the inductive effect, next is the mesomeric and resonance effect, electromeric effect, and the hyperconjugation, right? So what is the electronic displacement in the covalent bond? So basically the following four types of electronic effect operates in a covalent bond: inductive, mesomeric or resonance effect, electromeric effect, and the hyperconjugation. So we are going to study all these four in detail: inductive effect, mesomeric resonance effect, electromeric effect, and the hyperconjugation. Now, what is inductive effect? So basically, we have a two type of inductive effect. One is known as a negative inductive effect, and another is known as a positive inductive effect, right? So basically, this is due to electron attracting group, right? So whenever the electron attracting group are present, like a halogen, right? So it develop a positive charge on the chain and said to exert a negative inductive denoted by minus I, right? So when a negative effect comes into the picture, when the electron attracting group, or we many times we can say that whenever the electron withdrawing group are attached. So whenever the electron withdrawing group are attached to the carbon atom, it develop a positive charge on the chain and it is said to exert a negative inductive donated by minus I. So as we can see that, for example, if I'm talking about CH3 and Cl, right? So Cl being more electronegative, so it try to attract the electron towards itself. So this will show a minus I effect because this C become partial positive and this Cl become partial negative, right? So this will show, this will show a minus I effect. Now, what is the effect of this? So it decreases as one goes from the group, that is X electron attracting. For example, X, C1, C2, C3. So here in C1, we have a only partial positive charge of 1. Here we have a partial positive charge. And here we have a 3 partial positive charge. So as the distance between the electron withdrawing groups, that is X and the carbon increases, this effect will be minimized. So and after third carbon, change charge is almost negligible. So we can say that it decreases as one goes from the group, that is X. So as we move from the first carbon to the third carbon, their effect is decreases. Now, the another important note here, that is the DL configuration. So basically the configuration of an enantiomer is related to the standard glyceraldehyde order like NH3, NO2, FCOH, ClBr, IOH, and C6H5. So here we can say that the order is like NO2. So they're having a more electron withdrawing capacity. After this fluorine, then we have a COH, then we have a chlorine, bromine, OH, and benzene. So if I'm talking about the order of this, so we get the order like this, that is a NO2 having the high low electron withdrawing group, so it will show a greater minus I effect, followed by fluorine, carboxylic acid, chlorine, bromine, iodine, and last benzene. Now, what is a positive inductive effect? So this is due to the electron releasing group, or we say whenever the electron donating group is present. So this is for electron donating group, also known as electron releasing group. Similar, electron attracting group is also known as electron withdrawing group. Now, it develops a negative charge on the chain and said to exert a positive inductive effect denoted by +1. For example, let's see if the more positive element then carbon is attached to the carbon bond, then definitely carbon will be more electronegative. So it attract the electron towards self and they become partially negative charge. Similarly, Y become partially positive charge. So it develops a negative charge on the chain and is said to exert a positive inductive effect. It is denoted by +1. It also decreases as we away from the group, that is the electron releasing group. For example, C1 having the most negative charge, then C2, C3, and so on. Right? Now, order we can say that is a tertiary carbocation. If I'm talking about the tertiary carbocation, so these having the maximum, for example, this CH3, this CH3, and this CH3, right? And this is R. So this one having maximum. Why this is maximum? Because here the electron donating group is more. So as the number of electron donating group increase, plus I effect also increase, right? So more electron donating group is attached to this carbon will become more and more and more negative. So as the number of tertiary carbocation is showing plus I effect much more readily as compared to secondary, primary, and the CH3R. Right. So I hope this is clear to you. Okay. So what is the effect of this I effect? So basically, if I'm talking about the acidic nature, so minus I effect increase the acidic nature and decrease the basic nature, where the plus I effect decrease the acidic nature and increase the basic nature. So if someone says out of CH3, CH2, and NO, right? And one is CH3, CH2, and CH3, which will having more acidic in nature. So obviously we can say that here one electron withdrawing group is increased. So it will show minus I effect. So this due to minus I effect, right? So due to minus I effect, it will increase the acidic nature. So we can say that this one is much more acidic as compared to this. On the similar cases, if we have CH3, CH2, and NO2, and we have a CH3, CH2, and OH, and out of this we want to know which one will have OH2, or we have CH3, CH2, and NH2. And out of these three, if we want to know the correct order of basicity, which will behave as good basic, so we know that this will show minus I effect, this will show plus, and this will also show plus I effect, right? So as the plus I effect increase, basic nature increase. So out of these two, this one is number one, that is number two, and this is at number three. So this one is a much more basic in nature. Due to presence of this lone pair, they want to donate this. So we can say that basic nature increase with the increase in the plus. I hope this is clear to all of you. That is how acidic and basic nature are related to minus I effect and plus I effect. So if you increase the minus I effect, then acidic nature also increase. And if you if you decrease the minus I effect, then the basic nature, right? So acidic nature minus I effect increases and basic nature decreases if the minus I effect, right? So this is how we can actually understand this thing. Okay. Now let's move to the next effect that is called mesomeric effect, or we say sometimes also known as resonance effect, right? So what is this mesomeric effect or resonance effect? So basically in a conjugated system, pi electron shifting takes place consecutively, giving a permanent polarity on the chain. So in the conjugated pi conjugated system, pi electron shifting takes place consequently, giving permanent polarity on the chain. Now, what is positive mesomeric effect? So positive mesomeric effect means plus M effect. So a group or atom is said to be have a plus M effect when the direction of the electron displacement is away from it. So if the direction of electron displacement is away from it, then it is said to be a positive M effect, right? For example, here we can say that this will show positive M effect. Here you can say that the direction of this lone pair. So a group or atom is said to be a plus M effect when the direction of electron displacement is away from it, right? So they having positive, they having positive, they having positive. So this is also called as a resonance plus R effect, right? So similarly, in case of phenol, we have a diagram like this. So aniline, we know that aniline, they have donated this two electron to air, this will be double bond, and this electron transfer to the next. Again, this will transfer to the next, and this will take place at a resonance diagram. Right. So this is known as basically the positive mesomeric effect. Now, what is negative mesomeric effect? A group or atom is said to be a have a plus M effect when the direction electron is bent towards it. This will not plus M, this will be minus M, right? Okay. So a group or atom is said to have a minus M effect when the direction of the electron displacement is towards it. So when the direction of displacement towards it, that is known as to have a negative mesomeric effect. So how we get to know when the positive mesomeric effect will show and seen and where we have a negative mesomeric effect. So whenever the electron donating group, right? So whenever the electron donating group it is attached, then we always show a positive mesomeric effect because they have a tendency to donate the electron. So whenever the electron withdrawing group, electron donating group was present. So always remember this: electron donating group give rise to the positive mesomeric effect. On the other hand side, electron withdrawing group. So on the other hand side, electron withdrawing group give rise to the negative mesomeric effect, or we say minus M effect. Right? I hope this is clear to you. Okay, good. Now, this is called resonance energy. What is this resonance energy? So basically the difference in energy between the hybrid and the most stable conical structure is called the resonance energy, right? So it is a difference in energy between the hybrid and the most stable conical form. So here we can say that that is the total energy structure. This is the benzene, this is structure of benzene, and this is also the structure of benzene. So this is a resonance diagram of benzene where the shifting of this electron takes place, right? Here we can say that we have a the pi bond is shifting. The nature of this pi bonding is shifting. So we have a energy difference of 36 kilocalorie. So this is the resonance energy of benzene, or we say other chemical structures. So basically the difference in the energy between the hybrid. So this is the hybrid and the most stable conical form. So this is the most stable conical form and the hybrid. So the difference in the energy between the hybrid and the most conical stable structure is called the resonance energy. Right? Now, let's see the next one, that is electromeric effect. So what is this electromeric effect? So basically the complete transfer of pi electrons from one atom to another to produce temporary polarity on atoms joined by the multiple bonds. So basically the complete transfer of pi electrons from one atom to other to produce temporary polarity on atom joined by the multiple bond in presence of electrophiles is known as electromeric effect. So always remember this, that is a complete transfer of pi electrons from one atom to other to produce the temporary polarity on atoms joined by a multiple bonds in presence of an electrophile is known as electromeric effect. Now, the effect is reversibly and temporary. So this effect is reversible and also temporary in nature. Right. So this is all about the electromeric effect. That is the complete transfer of pi electrons from one atom to other to produce temporary polarity on atom joined by the multiple bond. Right. So it is a temporary effect. So what is positive electromeric effect? So basically pi electron transfer takes place from carbon to carbon as alkene, alkynes, etc. So this is a positive electromeric effect, which is takes place from p electron transfer takes place from carbon to carbon as alkene, alkynes, etc. Right. So we can say that here electrophile is added and electrophile is removed. So if you add the electrophile, it will become C plus C negative. If you remove the electrophile, it will become like this, right? So this will show positive electromagnetic effect. Similarly, what is negative electromagnetic effect? So negative electromagnetic effect means p electron transfer takes place to more electronegative atom like ONS joined by a multiple bonds, right? So the pi electron transfer takes place to more electronegative atom, oxygen ONS, and joined by the multiple bond. So this will give rise to the negative electromagnetic effect, right? Now, the next thing is hyperconjugation. So what is this hyperconjugation? So basically the delocalization of sigma electrons, also known as sigma pi conjugation or no bond resonance. So it is a permanent effect. The first important thing here is it is a permanent effect. So basically the delocalization of sigma electrons, also known as sigma pi conjugation or no bond resonance occurrence. So it is basically occur in alkene, alkyne, free radical saturated type and carbonium ion that is saturated type. What is the condition for the hyperconjugation? Presence of alpha H with respect to a double bond, triple bond carbon containing a positive charge in carbonium ion or unpaired electron in the free radical. So presence of alpha H with respect to the double bond, or we say triple bond carbon containing a positively charged in carbonium ion or unpaired electron in the free radical. So these are the conditions. For example, we can say that this is CH2, CH2. There is a, this is a group. This is the presence of alpha hydrogen. So this is alpha hydrogen. Again, in this we have a group. This again we have a presence of this alpha hydrogen. So either this H or we say this H or we have a three this H, right? So no, number of hyperconjugation structure is always equal to number of alpha hydrogen. Hence, in above example, structure 1, 2, 3, 4 are the hyperconjugation structure. That is the H structure, right? So we have a possibility like either three, that is 1, 2, and 3. So three alpha hydrogen are possible. So we have a possibility of this three, right? So always remember the number of hyperconjugation structure always equal to number of alpha hydrogen. Hence, in the above example, a structure of 1, 2, 3, 4 are the hyperconjugate structure, or we say H structure, right? Now, okay. So what is the effect of hyperconjugation? So basically the bond length, if I'm talking about the bond length, so hyperconjugation also affect the bond length because during the process, the single bond in the compound acquires some double bond character and vice versa. The effect of higher bond length. So hyperconjugation also affect bond length because during the process of single bond in compound acquires some double bond character and vice versa. Similarly, dipole moment. Since hyperconjugation caused this development of charges, it also affects the dipole moment of the molecule, right? So since the hyperconjugation caused this development of charges, it also affects the dipole moment of the molecule. Now, if I'm talking about the stability of the carbanion anion, then the tertiary carbon ion is much more stable as secondary and primary. And the free radical, then the tertiary free radical is much more stable than the secondary and this, right? So this is the stability. Now, reactive intermediates. So, species and their stability. So we know that species, you have a carbocation, carbanion, and the free radical. So if I'm talking about the geometry, sp2 hybridized, a carbocation having sp2 hybridized with a planar structure and bond angle are of about 120 degree. So there is a vacant unhybridized p orbital, which is in case of CH3 plus lie perpendicular to the plane of carbon hydrogen bond. Stability. So any structure feature which tends to reduce the electron deficiency as the tri-coordinate carbon stabilize the carbocation. The order is like 3 to 1 degree and carbocation. Now, similarly, carbon and sp3 hybridized with the one unshared pair occupy an apex of the tetrahedron pyramidal structure similar to those of the amines. So any structure like 3, 2, 1. So maximum stability is 3 CH3, then primary, for secondary, and then tertiary. Similarly, sp2 hybridized with the planar trigonal structure and the sp3 hybridized with the pyramidal structure. So hyperconjugation follow this order 3 to 1. So for the carbocation free radical order will be same like 3 to 1 degree. And for the carbon and order of like 1 degree, 2 degree, and 3 degree. So these are the reaction intermediates, right? So this is all about the effect, that is I effect. So already studied about the I effect. And next is you already studied about the I effect and resonance effect, mesomeric effect, and the hyperconjugation, right? So now from on now today onwards, now from today, we are going to study isomerism as well. So what is isomerism and all, right? Okay, so just give me 2 minutes, then we're starting with the isomerism, right? Right. So what is isomerism? So we know isomerism, we can classify isomerism as well. So how will you classify the isomerism? So isomerism is basically classified as a structural isomerism and the stereoisomerism. So in a structural isomerism, basically we have chain isomerism, position isomerism, functional isomerism, metamerism, tautomerism, ring chain isomerism. So in a structural isomerism, we have a chain isomerism, position isomerism, functional isomerism, metamerism, tautomerism, and the RCI, that is a ring chain isomerism. Right. Similarly, in the stereoisomerism, we have a like a geometrical isomerism, optical isomerism. Right. So this is all about the isomerism, right? So no issue in this. That is the chain, position, functional, metamerism, tautomerism, ring chain isomerism. So stereo isomerism like geometrical isomerism and the optical isomerism. So let's see about the structural isomerism. So basically isomerism, description and their example. So in the chain isomerism, this type of isomerism arises from the difference in the structure of carbon chain, which forms the nucleus of the molecule, right? So this type of isomerism arises from the difference in the structure of a carbon chain, which forms the nucleus of the molecule, right? Now, similarly, position isomerism arises. It is the type of isomerism in which the compound possessing same molecular formula but different in their properties due to the difference in the position of either the functional group or the multiple bond, or we say the branch chain attached to the main carbon chain, right? Similarly, what is functional isomerism? So in this type of isomerism, two compounds have the same molecular formula but possess different functional group, right? What is metamerism? So this type of isomerism is due to unequal distribution of carbon atom on either side of the functional group in the molecule of the compound belonging to the same class. And in tautomerism, it is the type of isomerism in which two functional isomers exist together in equilibrium. The two forms existing in the equilibrium are called tautomerism, right? For example, butane and isobutane, and propyl alcohol and isopropyl alcohol, diethyl ether and butyl alcohol are an example of functional isomerism. So metamerism, we know the example of metamerism like methyl propyl ether and diethyl ether, both have the molecular, right? And the acetoacetic ester has the two tautomer, one has keto group, another has the enol group. So these are the example of tautomerism, right? Now, let's see about some geometrical isomerism. So which type of geometrical isomerism they generally show? So basically the isomer possess the same structural formula containing a double bond and differ only in respect of arrangement of atoms or a group about the double bond, right? So basically the isomer possess the same structural formula containing a double bond and differ only in respect of the arrangement of atom group about the double bond. This isomerism is shown by alkenes or their derivative in which two different atom or group are attached to each carbon containing the double bond. So basically in this isomerism is shown by the alkenes or their derivative in which two different atoms or group are attached to each carbon containing the double bond. Thus, the compound having the formula like ABC double bond CX. What do you mean? This mean if we must have a restricted rotation system like double bond, and we were two different group like A, B, and this is X and Y. Right. So this will show geometrical isomerism. Thus, the compound having the formula like ABCCXY or the simple structure, just like C and this having AB and this is also having AB. So this will also can show. So just remember that two different group present on only one carbon atom, right? So for example, if we have a structure like this, I have a CAA and this have B and C. So this one shows geometrical isomerism where this isolation by looking the derivative is the two different group or atom attached to the each carbon atom. So each carbon atom it must have been two different group or two different atoms, right? And to form and exhibit geometrical isomerism. So these are the important condition for the geometrical isomerism. The first, this isomerism is shown by the alkenes or their derivative in which two different atoms or group are attached to each carbon containing the double bond. Thus, the compound having the formula ABC and CXY or the simple structure like ABC, CAB occur in the two forms and exhibit geometrical isomerism as well. So these are the example of the geometrical isomerism, right? Now, the example is such as malic acid. So we can observe that here we have a H and COS, so two different group. Here also we have a two different group. So this will show geometrical isomerism. This will also show. So this is the cis form and this is the trans form, right? So this is a trans form because these two H are equal and opposite to each other, right? And this is also. So this is the trans form and this is the cis form. Similarly, this will also show Z and E isomerism, like this is HBr, HBr, BRH, and HBr. So this will also show ZNE isomerism. Now, this is an example of we have a cis 2 cis 4 hexadiene, that is cis 4 cis 2 hexadiene, and this is a cis 2, but here we have a cis 2, but here we have a transform, right? Here we have a transform. So cis 2 trans 4 hexadiene and trans 2 trans 4 hexadiene. So these are also geometrical isomerism. Now, the trans isomer of alkenes are usually more stable than their corresponding cis isomerism. Why? Why the trans isomer of alkene are usually more stable than their corresponding cis isomer? Because the trans isomer have normally less dipole moment than their corresponding cis isomer, right? So basically the trans isomer of alkene are usually more stable than their corresponding cis isomer, and the trans isomer have normally less dipole moment than their corresponding cis isomer. Now, the trans isomer has greater symmetry than the corresponding cis isomer, right? And thus it packs more easily in the crystal lattice, hence has a higher melting point. So we can say that the trans isomer possesses higher melting point. Why? Because the trans isomer has a greater symmetry than the corresponding cis isomer. Thus it packs more easily in the crystal lattice and hence has a higher melting point. We can also say. Right. Now, if I'm talking about the optical isomerism, so optical activity, basically the property of substance rotate the plane polarized of light. Specific rotation, that is the number of degree of rotation observed when the light is passed through the 1 decimeter or say 10 centimeter of its solution having the concentration of 1 gram per milliliter. So we known as a specific rotation, right? So in optical activity, we have some important term like a levorotatory or we say minus form. So what is it you mean by this form? So it rotates the plane, it rotates the plane of polarized light to the left. So if they rotate the plane of polarized light towards the left, then it is known as a levorotatory. Similarly, what is dextrorotatory or plus minus form? So if they rotate the plane of polarized light to the right, then it is known as dextrorotatory. Similarly, an inactive form which does not rotate the plane of polarized light at all, this mixture of equal amount of plus and minus form, and hence it is called optically inactivity, right? So this is called racemic mixture. So basically, what is racemic mixture or plus or minus eye effect? If we mix both this above, levo and dextrorotatory. So an inactive form which does not rotate the plane of polarized light at all, and this is the mixture of equal amount of plus I and minus I, and form, hence it is a optically inactive, right? So what is a symmetrical carbon atom? So basically a carbon atom which is attached to a four different atom is known as asymmetrical carbon atoms, right? So here chirality, we also need to know what is chirality, because this play also a very important role here. That is what is chirality, right? Right? Okay. ठीक है. So we have a form like chirality, that is all organic compound which contain an asymmetric carbon, right? So all organic compounds which contain a asymmetric carbon, that is CABDE. It means they having four different, four different group on the carbon atom are said to be chiral and exist into two tetrahedral form, right? And they are exist into two tetrahedral form. Right. So all organic compounds which contain an asymmetrical carbon. For example, if we have a C and they are surrounded by H, they consist CH3, Cl, and F. So they are said to be asymmetric, or they are said to be chiral carbon, right? So the condition for the chiral carbon are all organic compound which contain a symmetrical carbon, that is A star, ABD, atom are chiral and they are exist into the two tetrahedral forms. First, a molecule must have a chirality in order to show optical activity. So a molecule must have chirality, right, in order to show the optical activity. So in order to show the optical activity, a molecule must have chirality, they must show chirality. So they are the as a sufficient condition for the molecule to show optical isomerism, right? Chirality. Now, what is an enantiomer? This is the two optical isomerism which are non-superimposable mirror image of each other. They are said to be enantiomer. For example, here we can say that Cl and Br, right, and H and F. So these are said to be a non-superimposable mirror image of each other, and they are called enantiomer, right? So it is meso compound. So compound containing two or more chiral carbon which do not show optical activity due to presence of center symmetry indicated by the thick bond, right? So compound basically containing two or more chiral carbon which do not show optical activity due to presence of center of symmetry. They are indicated by the thick dot. Now, the compound which have a asymmetrical molecule with one or more chiral center. So the compound which have a unsymmetrical molecule with one or more chiral center. In such compound, if n is the number of chiral carbon, then how will you find the number of optimally active isomer? We can find as 2 raised to the power n. So if such compound, if n is the number of chiral carbon, so if n is equal to 2, its value is 4. If n is equal to 1, then its value is 2 only. Now, number of racemic form, that is R, which is nothing but equal to A by 2, and number of meso form is equal to 0 only. Right. Similarly, compound having a symmetrical molecule, compound having the chiral carbon, but molecule as a whole is achiral. So compound having a symmetrical molecule, compound having chiral carbon, but molecule as a whole is a achiral. So for this, the compound with the even number of a carbon atom, in such compound, if the number of chiral carbon is n, then we have a formula for calculating like A is equal to 2n minus 1, or R is equal to A by 2 and M is equal to this. So we can calculate A, R and M, right? So A means the number of optical active isomer, R means racemic mixture, M is mesoform. So we can calculate. Similarly, if the compound with the odd number of carbon atom, in such compound, if N is the number of asymmetric carbon, then the total isomer are given by 2 raised to the power N, or we say M, R, A and R, we can calculate like this, right? Now, so inactivity of the meso or tartaric acid by internal compensation. So we can say that the force of rotation due to one half of the molecule is balanced by the opposite and equal force due to the other half of the molecule. And the optical inactivity so produced are said to be due to the internal compensation. And it occurs whenever a compound containing two or more, right? Now, what is a Fisher projection? So this is the another way of presenting the optical activity. So basically the Fisher projection representing three-dimensional structure on the two-dimensional surface. So in the Fisher projection, basically we represent the three-dimensional structure in 2D, two-dimensional surfaces. A symmetric carbon atom drawn in a prescribed orientation and then projected into a planar surface. And the planar formulas of the symmetric carbon are obtained by placing it so that the two substituents are horizontal, right, and projected out towards the viewer, shown by the thick wedge-like modes, while the two other substituents are the vertical one, right? So let me show you. Just wait for a second. Right? So this is how we can actually represent the Fisher diagram. So this is the Fisher representation, right? For example, this CH3, CCOH and OHNH, right? So this is acting like this CH3 and CH3, these two are in plane, and this H and OH are acting outwards or inwards, right? So these are the Fisher projection. So this is a Fisher projection. We have a CH3, COH, H, and OH. So just rotate this line, this vertical line, and this horizontal line. So this horizontal line represent which is acting outwards, and this vertical line represent inwards, right? So this is how we can represent. Now, what is DL configuration? So basically, the configuration of the enantiomer is related to a standard glyceride. So the DL configuration means the configuration of an enantiomer is related to a standard glyceraldehyde. So this is plus minus glyceraldehyde, or we say D configuration, and this is the Al configuration. OH is acting left hand side, right? This is known as the Al. So if the configuration of the symmetric carbon atom of the compound can be related to D plus glyceraldehyde and it belongs to the D series. And by the convention of sugars, the configuration of the highest number of symmetric carbon is referred to as the glyceraldehyde to determine the overall configuration of the molecule. Now we have another one system that is called RS system. RS system. So the sequence rule to determine the order of priority group are basically the atom or group directly bonded to the asymmetrical carbon are arranged in order of decreasing atomic number and assigned per priority 1, 2, 3, 4 accordingly. Thus in a chloro-bromo-fluoromethane, right? Chloro-bromo-fluoromethane, the substituents bromine, which having atomic number 35, chlorine atomic number 17, 9, and 1, give the order of priority as bromine. We give the priority of 1 is bromine, then chlorine, fluorine, and then hydrogen. When two or more groups have the identical first atom attached to the symmetric carbon, the priority order is determined by considering the atomic number of the second atom. And if the second atom are also identical in the third atom along the chain are examined. Right. If the first atom of the two groups have the same substituent of higher atomic number, the one with the more substituent takes place priority. The CaCl2 has a higher priority than the CH2 and C. Right. So a doubly or triply bonded atom A present in a group appending to the symmetric carbon is considered equivalent to two or three singly bonded as respectively. Thus, R we say is equal to A. So if in a molecule order of priority group A, B, C, D, that is A is greater than B is greater than C is greater than D, and right. So this is all we can determine the RS configuration. On the similar basis, we have a next and last, we have a distereomers. So basically the stereoisomer, which are optically active isomer, but not mirror image are called distereomers. So distereomers have a different physical property, thus they have a different melting points, boiling points, solubility in a given solvent, density and refractive indices, right? They also differ in the specific rotation. They may have the same or opposite sign of rotation. Like geometrical isomers, the diisomers may be separated from each other by the fractional distillation due to their difference in the boiling point, by fractional crystallization due to their difference in solubility, and by the chromatography due to their difference in the molecular shape and the polarity. Right. So this is all about the important topics of this chapter. Now we are going to solve some numerical that is some numerical that were come in the previous year exam, right? So we're trying to do some PYQ related question related to this chapter only. So I hope till we cover almost the isomerism part, optical and geometrical isomerism parts, and the types of fission we already cover, and the displacement, that is electronic, inductive, and the mesomeric effect. So we already covered this thing, right? So let's do some question that were really asked in the previous year examination, so that we can able to solve some numerical related to this, right? So after 2 minutes, and we start with the question. Right. So let's start with the some PYQ question. So we have a first question like this. Which of the following molecule is the pure form that are unstable at the room temperature? So we know that according to the Huckel's rule, basically the aromatic compounds are stable and anti-aromatic compounds are unstable. So we have to find the condition for anti-aromaticity and the aromatic. So those which are anti-aromatic in nature are said to be the unstable. Right. So in general form, if we look at the Huckel rule, it said that the compound that have the 4n, right, 4n decoys and pi electron in the closed loop. So if you observe this, the option B and C, right? So the molecule given in option C also follow Huckel's criteria for anti-aromaticity, right? So it will follow the Huckel's criteria. Let me write. Huckel's criteria for anti-aromaticity. So both the compound B and C, they are follow the Huckel criteria for the anti-aromaticity. Thus, we can say that these two compounds are unstable, right? I hope this is clear to you. So basically, we know that now what is how will you calculate this aromaticity? So we know that this will contain 4n plus 2 pi electrons, right? 4n plus 2 pi electrons, and it comes out to be integer form, right? So basically, the we can you use to calculate this by just substitute in order to determine the number of pi electron in case of aromatic system. The following formula we use, that is 4n plus 2 pi 4n plus 2 pi 2. In order to determine the case of electron that's anti-aromatic system, the n is equal to 4n. So we can use this n is equal to 4n. Right. So let's understand through this 4n plus electron and what is this. So in case of we just opening a question. Yeah. Right. So this will follow the rule like 4n rule. 4n rule is for the this is rule for the aromatic behavior. And this is for the anti-aromatic. Right. So all this following this rule, this is 2 plus 4, 4, this is 2 plus 2. Right. So this will 4 electrons. So the B and C, these two are unstable because they follow the Huckel criteria for the anti-aromatic. Right. Now, the number of resonance structure for N is. So you have to calculate the number of resonance structure of N is. Right. So here we get the N. So what is, first of all, what is N? And then we get to know what is the resonance structure of N. So what is N beta? What happened when this is treated with NaOH? So we'll get like this. Right. So this is what we get. Okay. So yeah. So this is what we get. So what is the resonance structure of this? So we can draw the resonance diagram of this, like this will be here and this will be converted into, again, this is benzene, right? And this is, again, we have a negative charge. So this will become negatively charged. This will become double bond, right? This is going to this part. This is already having positive, positive, positive. Yeah, right? So this is something like this. So we get the negative charge. So again, in the next diagram, what we have, so we have with right. So this is, again, this is, and we have, yeah. So we have a negative charge here, and this two electron is double bond, and this is double bond O. Now, in the again next case, what we have, so in the next case, we have this negative charge. So delocalization of this negative charge will take place, right? So we have this charge. Again, we have this charge. Oh, so sorry. Yeah. And this is very much similar, just like the previous one. Okay. So this is what we have. So this is the fourth diagram. So on total, if you draw the diagram, how many diagrams we have? That is one, this is having two, this is having three, this is having four, and just reverse of this also, we get only all five more diagrams. So total we have nothing but how many diagram we have? That is six, seven, eight, and nine. So total we have a nine. So the number of resonance structure of N is 9. So we have a total 9 resonance structure. Just like this, if you draw the further next five diagram, we get the structure like this. The total we have a 9 structure similar to this. Now, the next question, this is also very important. The total number of lone pair of electron in the melamine. So this is the structure of the melamine we have. So they are asking total number of electron in the melamine. So in this, we know this having which having a lone pair of electrons. So we know that nitrogen having 5 electrons, 2 comma 5. So out of 5, here we can say that 2 and 1, 3 electrons were participating. So these two, right? So how many lone pair of electrons? So the total number of lone pairs of electron in this have a 6, right? So total number of lone pair of electrons in the melamine is 6. Sometime this type of questions also come like total number of lone pair of electron that takes place in the resonance. Then also we can say that 6 electrons, or we say how many lone pair are takes place in the resonance. If someone asks how many how many lone pair of electrons, how many lone pair of electron takes place in resonance of nitrogen. So how many lone pair of electron takes place in resonance of nitrogen? So we can say that 3 lone pair, like this one and one N2 and N3. So total we have a 3 nitrogen, of which lone pair of electron will takes place in the resonance formation, right? So this is also clear. I hope this is also very easy. Good. Now let's move to the next question. That is, in this question, what we have, that is, we have to calculate the total number of contributing structures showing hyperconjugation, right? So we have to calculate the total number of contributing structures showing hyperconjugation involving the CH bond for the following carbocation, right? So for the following carbocation, we will have to calculate the total number of contributing structures showing the hyperconjugation involving this CH bond, right? Now, there are six atom on the carbon atom adjacent to the carbon atom containing a positive charge. So there is six adjacent hydrogen, that is three here, and this will be right. So we can say that there are six hydrogen atoms on the C atom. On the C atom adjacent to the carbon atom, right? Adjacent to carbon atom containing a positive charge. Okay. So there are six hydrogen atom on the carbon atom adjacent to carbon atom containing a positive charge. So how can we draw this? We can draw as, right? So this having the positive charge. So we have a carbon like how much of hydrogen we have? So there is a one HA. We can write. HB we can write, and this is HC. So we have a three hydrogen HAB, HAC, right? Similarly here we have a hydrogen like HT, right? And one CH3 group is also here. We have a HE, and here also we have HF, right? So in this positive charge, we can observe carefully. We have CH2, we have a one CH3 and two hydrogen atom, that is CH2, CH2, so two, and one 3 and one CH3 bond. So this carbon, so total, and here also we have a one HF bond, right? Because carbon double bond, triple, and when we have a hydrogen. So how much hydrogen? The total number of contributing structures showing hyperconjugation involving CH bond for the following carbocation is, that is 1, 2, 3, 4, 5, and 6. The total is 6. So there are 6 hydrogen atom on the carbon atom adjacent to the carbon atom containing a positively charged. So I hope this is clear to you. Right. Now, the next is the carboxylic functional group COH is present in. So, which of the following carboxylic functional group is present? Picric acid? No, in picric acid we have a structure like NO2, NO2, and NO2. So, this is the formula of the picric acid, that is 2,4,6-dinitrophenol. So, in this COH group is present. Ascorbic acid also we do not have this. Barbiturate acid we also don't have a. So what is? So we are left with the aspirin, right? So aspirin having carboxylic functional group, right? So the carboxylic functional group COH is present in the aspirin. Always remember this. Now the next question, that is question number 6. That is, which among the following compound is the most acidic? So we already studied this thing. It's called the acidic nature. Minus I effect play comes into the picture, and also the some ortho effect is also responsible. So if I'm talking about that is, let me draw the structure of each of the following. So we have a structure like para-nitrophenol. So structure of para-nitrophenol be like this is phenol, and this will become para-nitrophenol. Similarly, para-hydroxybenzoic acid. So para-hydroxybenzoic acid. So all the structure of benzoic, and we have a OH. So this is para-hydroxybenzoic acid. Now ortho-hydroxybenzoic acid, right? And para-tolic acid. So we have a structure like para-tolic acid. So how will you draw the structure of para-tolic acid? Right. So, which among the following compound is the most acidic? We know that acidic character increase whenever the electron withdrawing group is attached to it, it increases the acidic character. So, out of phenol and carboxylic acid, obviously we know that carboxylic acid is a good oxidant, good acidic in nature. Now, the question is, out of this and this, which one will have the good acidic character, right? So the main reason is due to the ortho effect, in which the ortho hydroxy acid, that is hydrogen, is attached to the oxygen of the hydroxy group. However, this hydroxide group is present at the ortho position. Ortho substitute benzoic acid are mainly mostly acidic. Always remember this ortho effect. So due to ortho effect, this that is ortho hydroxybenzoic acid, this will be the much more acidic, right? So due to this, why they are most acidic? Due to the stabilization of the intermolecular H bond with the outward electron donating resonance structure of OH. Let me draw the structure. For example, if I draw the structure like this, that is COH and this is OH, right? So what you will get in presence of H plus. Okay. So what the formation takes place? This one, this one, this one, right? And this is nothing but O, O, H, O negative, and this, right? So due to this, hydroxy acid is the strongest acid due to the stabilization of intermolecular H bond, right? So due to this reason, this orthohydroxybenzoic acid is good acidic in nature. Now, the next question number 7. Amongst the following, the total number of compounds soluble in the aqueous NaOH. So you have to identify the total number of compounds that are soluble in the NaOH, right? So for this, it will include the compound with either COH group or the phenolic OH group, right? So only these two group, either they will contain COH group or the phenolic OH group, they are soluble. So identify the one. So this is the OH COH group, that is number 1. Number 2, 3, and yeah. So this is the first group, and this is the phenol is also, right? So this is the phenolic group, OH, and this is also 3, and the next is COH 4. This will not contain the phenolic group, right? So this is the, yeah, this will not. So this is third, and this is fourth, right? So among the following, the total number of compounds which are soluble in aqueous NaOH. So only 4 compounds. Only 4 compounds which contain which 4 compound. So it will include, right, it will include compounds with either COH group, or phenolic group, right? So it will include compound with either COH group or the phenolic group. So any compound which contain the COH group, phenolic group, they are soluble in aqueous NaOH. So the correct answer is 4. Now, question number 8. So this is also very important. So what the question asks, the correct stability order of the following resonance structure is, right? So the stability of the conical structure are decided by the following factors. First, the neutral structure are the most stable. The first important state is neutral. Neutral structure are most stable. Right? So the neutral structure are most stable one. Always remember this point. That is the neutral structure are the most stable one. The important one is this. Next, greater the number of covalent bond, the greater is the stability, right? So greater the number of covalent bond, greater it's the stability. So the important note is here, if you increase the number of covalent bond, greater is the number of covalent bond, greater is the stability. So number of covalent bond is directly proportional to the stability, right? So the number of covalent bond is directly proportional to the stability. So greater is the number of covalent bond, greater is the stability, right? So the first one is neutral structure are the most stable. Second one is the greater the number of covalent bond, greater is the stability, right? Now, third one is a structure with a negative charge on the more electronegative atom will be more stable, right? So a structure with the negative charge on the more electronegative atom will be more stable. So the structure with a negative structure with a negative charge. So the structure with the negative charge on the more electronegative. So the structure with the negative charge on a more electronegative atom will be more stable. So remember this point as well. Structure with the negative charge on the more electron atom will be more stable. Now, the charge separation like charges should be at the maximum distance. So charges should be at maximum distance. Charges should be at maximum distance. So these points are important to identify the correct stability order of the following resonance diagram. The first one is neutral structure most stable. So out of this, which of the following is the neutral stable? So almost right. So hence the stability order is one. Because we have a positive and negative, they are neutral to each other. So we have a first one, number of covalent bonds. So they will form 1, 2, 3, 4. So number of covalent bond is equal to right, four covalent bonds they will form. So we can say that structure with a negative charge on the more negative. So more negative here nitrogen, so we have a negative charge. So we can say that the first and the third. The first, third, and then second and fourth. The option is B. So which option is correct? That is option number B. So option number B is absolutely correct. That is first, having a stability of the first structure is more than third, and least stable is fourth. Because in this we have a positive charge on the most electronegative elements of the cell. Now, the correct order of the acidity order of the following. So you have to identify the acidic order. So we know that here electron withdrawing group is attached. Here also electron withdrawing group is attached. Here one electron donating group is also present, right? So if I'm talking about the acidic nature, so which of the following is the more acidic nature? So obviously that is the benzoic acid, right? Benzoic acid is the most, and after third we have a second, right? So we have a third, we have a fourth. Then we also have a benzoic acid. So third and fourth, right? And next is second and then one. So the order like A. So the first one is the most important one is benzoic acid. Then after this, toluene benzoic acid, toluic acid, and the next one is this one, parachlorophenol, and this one is a phenol. So this is the correct order for this, right? Now, the question number 10th is the compound that does not liberate CO2 on treatment with the aqueous sodium bicarbonate solution. So you have to identify the compound that does not liberate CO2 on treatment with the aqueous, right? So let's see now if I'm talking about on aqueous sodium bicarbonate. So NaHCO3, it decomposed to give Na plus HCO3 negative. So this HCO3 negative is decomposed by acid releasing CO2, right? For example, HCO3 negative, it will accept H plus, it will form H2O plus CO2. So in this question, they're asking the compound that does not liberate CO2 treatment with the aqueous sodium. So if acid is a stronger acid than SO3, the CO2 is released. Phenol is less acidic and thus does not liberate CO2 with NSO2. So we can say that phenol, carboxylic acid, that is phenol, which is less acidic, right? So if the acid is stronger than carbonic, SCO3 negative is present, then CO2 is released. The phenol is the less acidic, then SCO3, then the phenol does not release, right? So this is the correct one. Okay. So this is how we can solve this question. So we already covered lots of questions related to this chapter. That is the we already discover or cover all these 10 questions from this chapter, right? That is what is this all about. So quickly revise this all this thing. So the important note here is that is a bond fusion. That is we study about the bond fusion. That is a homolytic and heterolytic fusion. So basically homolytic fusion exists between the two atom having the same electronegativity difference, and the heterolytic fusion takes place between the two atoms having the different electronegatividity difference, right? Now, the reaction involving the radicals tends to occur in the gas phase or in the solution in the non-polar solvent while catalyzed by the light. Similarly, when the reaction involving the ionic intermediate takes place directly in solution in the polar solvent because of the greater ease of separation. Now we have a electronic displacement in the covalent bond. So total we have a 4 types of electronic displacement in the covalent bond, like in an inductive effect, mesomeric and resonance effect, electromeric effect, and hyperconjugation. So you need to remember all these 4, that is inductive, mesomeric resonance, electromeric, and the hyperconjugation. So inductive effect, basically we have a 2 type, that is the negative inductive effect and the positive inductive effect. So in the negative inductive effect, we have an electron withdrawing group attached to the carbon atom. And then the positive, we have a electron releasing, that is electron donating group attached to the carbon atom. So it develop a negative charge on the chain and is said to be exert a positive inductive effect denoted by plus I. Now it also decrease as we go away from the carbon, but this case is a value in both the case whether it is a positive or negative. Now the important note here, minus I effect increase the acidic nature and decrease the basic nature, where the plus I effect decrease the acidic nature and increase the basic nature, right? Mesomer effect, we have a positive measure also known as the resonance effect. So plus M effect when the electron donating group is attached, and minus I effect when the electron withdrawing group is attached. This is the resonance energy. So electromagnetic effect, we have a positive and negative electromagnetic effect. So these are the temporary effect, right? Hyperconjugation. So basically in hyperconjugation, the delocalization of sigma electrons, also known as the sigma pi conjugation or no bond resonance. So very important to note, no bond resonance, this is known as, it is a permanent effect and it basically occurs in alkenes, alkynes, and free radical. And presence of alpha H with respect to a double bond, triple bond, carbon containing a positive charge in carbanion ion or unpaired electron in free radical. Like here we have a 3 alpha hydrogen, uh, which can contribute to the 3 hyperconjugation structure. So what is the effect? That is the hyperconjugation also affect the bond length because during the process of single bond in compound requires some double bond character and vice versa. Since hyperconjugation causes the development of charges, it also affects the dipole moment of the molecule. The stability, if I'm talking about the stability, then the tertiary, secondary, and primary order they will follow. Now, carbocation having sp2 hybridization, carbon having sp3 hybridization, and the free radical also having the sp2 hybridization. Right, the order is like 3 to 1, and here 3 to 1 again. But in carbon order must be 1 to 3. In isomerism, we study different types of isomerism like chain isomerism and the stereoisomerism. So chain isomerism further classify chain isomerism as the chain, position, functional, metamerism, tautomerism, and the ring chain isomerism. Similarly, in stereoisomerism, we classify as the geometrical and isomerism, right? So these are the detailed explanation of all the structural isomerism. We already discussed this thing. Geometrical isomerism, to important note here, it should be restricted rotation system. It means a double bond and in which 2 different groups must be present. If the 2 different group is not present, then it will be produce a problem for this, right? So 2 different group must be present in order to release the things. Okay. Now the isomerism shown by the alkenes or their derivative in which 2 different atoms or groups are attached to each carbon containing the double bond. So these are the some essential feature for the geometrical isomerism you must know, right? So I hope this is clear to you. Good. So the trans isomerism of alkanes are usually more stable than their corresponding cis isomerism, and the trans isomer have normally less dipole moment than their corresponding cis isomerism. So we already studied this thing. We have a LIGO-rotatory chirality. So we have a 2 feature for the chirality, right? Okay. So at a molecule must have a chirality in order to show optical activity. The enantiomers. So 2 optical isomerism which are non-superimposable mirror image of each other. So they are called the enantiomers, right? So this we already cover all these things. So I hope And in last, we already covered some important numerical related to this chapter as well, right? So this is all for today. Now we can cover next chapter in the next class. Tell you revise this all these things so that you can able to solve question related to this and try to solve much question as you can, right? So let's meet on the next class.